Hello again. In this video, I will show you the part 2 of the do-it-yourself NAPSAC. And this is numerical adjustable power supply and charger system I built. This is the second iteration. In the second iteration, I use a 70 volt, 25 amp, DC to DC buck converter. The first generation, I used a 60 volt, 20 amp buck converter also. And this was done about 2 years ago, and it's causing slightly degradation right now. Let me show you what it is. And this is the very first generation. Right now, it's charging a cell that I have in here, a single cell that I have in here. And in this iteration, I actually have two power supply independently controlled. This one is a power supply, basically analog control. And this side is the digital numerical control. I really like the numerical control because I could dial in the voltage or current and it would not drift. The analog control would drift from time to time. One problem with this power supply is the noise. This is very noisy because I use a blower instead of a fan. This is the blower. Try to save some space. The other problem I have with this is the display kind of aging, and the numerical readout does not look very good, so I have to prop it up in an angle in order for me to see it. And the noise is really not very good. So let me turn it off to make it quieter in here. Okay, so I turned that off. And right now, this is powered by the battery I'm charging, because I don't have a reverse flow back ideal diode in this system. So in order for me to kill it, I have to stop charging it. Okay, now the display is off. So the third problem I have with that power supply is this is a 24 volt, 15 amp AC to DC power supply. About a week ago, the MOSFET was overheated and it got burned. You can see the burn mark in here, and both of them were cracked. So I replaced the 15 amp with a 20 amp power supply. This is a 20 amp power supply. Again, this is 24 volt, 15 amp. And I replace it inside with a 20 amp, 24 volt power supply in there. In the new design, this is a 25 amp, so I could charge at a higher current, which is very good. Even though this could go all the way to 70 volt, but since I'm mainly using it to charge a 12 volt battery, so I don't need to use it all the way to the 24 to the 70 volts. So the building blocks of this system is I have a 25 amp and 24 volt power supply, and I could max it out to 27.6 volt, and that would feed into a DC to DC buck converter that I showed you earlier, but I only use it up to 25 volts. And that would go to the low terminal. The low terminal would feed the low, and on the other branch it goes into a ideal diode. The ideal diode has already been talked about in part 1 of the video, and it will feed to the battery terminal, so that there's no backflow from the battery back into the system, like you saw in my first generation power supply. And with that, I also want to mention, instead of using a blower, I use a fan. And this fan is also temperature control. So it's the fan speed is proportional to the temperature of the power supply to reduce noise. And earlier you could hear the noise of the blower. Now let me turn it on. And this is the noise level of the fan is a lot more quieter. And I could also turn on the control display. So right now that's turned on, the control display, but the power supply is still off right now, it's still off. And let me show you what's inside. So inside here, this is the fan, and this is the speed controller, proportional to the temperature. And I have an NTC temperature probe that I put in this board. This board already comes with a temperature control to control its own internal fan, but I added another fan to control the overall exhaust fan. And packaging is a very challenging part of this project. As you can see, the space is very, very tight. Everything is limited. But finally, I did get it to fit everything within with no problem. So this is the fan speed control, and this is a 24-volt fan, and the DC to DC converter. This is the DC to DC converter, and the low terminal. This is the low terminal. This is a low terminal. This is also the low terminal. This is for high current. This is for low current. And then I have the ideal diode, and this is the ideal diode that I modified to make it work at 25 amp. So this is the ideal diode. And then the ideal diode would feed the battery terminal. So the ideal diode would feed, this is the battery terminal, and this is also the battery terminal. So this is have reverse flowback protection. This does not, and this is the negative terminal share between the two. Okay, the next, let's take a look at the speed controller. And the fan speed controller is pretty simple. Basically, it's a LM338 voltage control, and it has two resistors. And resistor 1 is replaced by NTC 2 kilo ohm temperature sensor, and resistor 2, instead of an adjustable resistor, is replaced by a 10 kilo ohm fixed resistor. So this is the data I tested, and the horizontal axis is the current, charging current. So I have 0, 5, 10, 15, 20, 25 amp of charging, and the top line, the diamond, is the temperature of the NTC sensor. As you can see, from 20 degrees Celsius all the way to almost almost to 60 degrees Celsius. At the same time, you can see the power supply voltage to the fan is also increasing. So when the temperature is hotter, the fan voltage is also higher to speed up the fan this way, and it controls quite well. And as you can see, at even 25 amp of charging, the temperature is under 60 degrees Celsius, and the over temperature protection currently is set at 85 degrees C. So there's a lot of headroom for this fan to work properly. And so that's it for the inside. Let me put it cover back on. And this 2 screw is also connected to the fan terminal, so I could use a voltmeter to measure the supply voltage of the fan. It will tell me what is the approximate fan speed is going in here. And on this side is the AC input, and also a lot of opening for air to go in here and come out from there. So let's do some charging right now, because this already comes with the ideal diode, so I could plug this battery in without any concern about damaging the power supply. So let me plug this in. Okay, so this is plugged in to the battery charging port, and let me adjust the charge voltage and current. Pretty easy to do. So adjusting, let's do the voltage first. So I put voltage set, and I adjust the let me go to 14.4 volt. So maybe I use this hand. 14.4 volt to charge the battery. Okay, so this is 14.4 volt to charge battery. I could turn off the blinking, and now I could adjust the current. And for the current, I push the SW to switch to the next digit and the next digit. I'd like to charge it at 25 amp if it allows me. Okay, so 25 amp and 14.4 volt charging. Okay, now if I just push the button, it will start charging. Okay, now it's charging at constant current at 25 amps. And we could also check, see how accurate this voltage is with a good voltmeter. So I have a voltmeter connected to this already, and the voltmeter is 13.89 volt, and this is 13.98. So this display and the voltmeter is off by about 0.1 volt. I could also calibrate a voltmeter, but right now it's not high priority at this point. So this is the charging voltage of the system before the ideal diode. There's a voltage drop in the ideal diode. So in order for me to measure the voltage drop on the ideal diode, I could undo this and plug the negative on this side. Now I plug the negative on this side, so I have the positive here and negative here. That way I will measure the voltage drop on the ideal diode, and the voltage drop on the ideal diode is 229 millivolt. 229 millivolt. It's pretty mild, but because we're charging at maximum current at 25 amp, that's why it's kind of high. Let me turn down the charging current to, let's say, 2 amps and see what happens. So 2 amp of charging current. And now the voltage drop of the ideal diode is only 21 millivolt. So 21 millivolt is pretty low, almost negligible. And many times the cable has higher voltage drop than the ideal diode itself. This also has a lot of feature that you could that we could see. So let's take a look at some of the built-in feature. If I push this once, it tells me what is the amp hour of the charging total, amp hour. I push it again, it tells me the watt hour of the charging energy. Push it again, it tells me how many hours or how much time I started charging the battery. I push it again, it tells me what is the temperature of the internal DC to DC converter board, and this is a good indicator how hot the system is running. So let me leave it at this temperature setting. Right now we're charging at 2 amp, it's only 27 degrees Celsius. And let's go back to 25 amp and see what happened. So let's go back to 25 amp. So this is 25 amp. And you can see the temperature went up from 27, now it's climbing to 32, and it continues to goes up to some steady state temperature because the fan speed is also picking up to cool the power supply. So the next piece of information I'd like to share with you is the part cost and the major parts. So I have a 24 volt 25 amp power supply, AC to DC power supply, about $35, and this is a very good power supply. It comes with a heat sink, not like this cheap power supply. It's just a thin aluminum housing, and this power supply actually comes with a extruded heat sink, and if you can see, the wall is an extruded heat sink. So the MOSFET has a lot of cooling surface in this power supply to keep the MOSFET cool. And then it has the 70 volt 25 amp computer numerical control buck converter, about $27, and then the fan and the controller is about $6, and the ideal diode is about $7, and this plastic box is quite expensive. It's $20, and then miscellaneous stuff is about $15. So the total of this do-it-yourself power supply is about $110. If I were to buy a power supply, like a nice power variable 30 volt power supply, the 20 amp version is $170 roughly. The 30 amp version is about $220. So it's a good saving, but I use a component that I know are good, and I build it to the way I like it. This alligator clip is quite expensive. It's $15 for this alligator clip to this NT60, I believe, NT60 connector. And let's check again on the temperature. The temperature now is 49 degrees Celsius from the beginning, which is 27. It's still very cool for the system. And this is pretty much I like to share with you. It's a fun project, even though it's time consuming and difficult to make electrically as well as mechanically. I hope you enjoyed this video. Have a good day. Bye bye.